We're going to start with section 6.1 today. It's called the set of rational numbers. And as we start this section, most of the chapters we start, you'll notice will start like this. It's pretty vocabulary heavy in chapter, like in the first section of the chapter. There's some examples and stuff, but we get more vocab, more writing kind of components. And then it's more computational as the chapter goes on. So we're going to start exactly in that fashion today with some definitions of what we mean by certain words, just to make sure we're all using the same ideas. So to start with, we're going to talk about fractions. Fraction is one way to describe a rational number. Specifically, fractions are any number of the form a over b, as long as b is not 0. So the way that this is described, it means you can use positives and negatives. A and b themselves could be decimals or fractions. They could even be things like pi, right? Or radical 2, square root of 2. They can be anything and be considered a fraction. The numerator is the value that's on top, and then the denominator is the value that's on bottom. Now, rational numbers, you'll notice, also talk about this in terms of a fraction, a over b. But there are some conditions in order for it to be considered a rational number. The a and the b are actually integers. Now, that means that anything that happened to be fractions and decimals and so forth before may have the ability to be changed into an integer and still be rational. But not everything can. And that rules out things like pi and square root of 2. So rational numbers don't include things that can't be changed into integers. Okay? So we'll talk more about changing values into things that are different forms of fractions as we go. There are 4 uses of rational numbers that we're going to talk about. That doesn't necessarily mean that this is all the 4 there are, but they're the 4 that are the most common. One use of rational numbers is for solving equations. So, for example, if I had the equation 2x equals 1, if I only have integers, right, positive and negative whole numbers, there's no solution for this. Because if x is 0, 2 times 0 is too small. And if x is 1, then 2 times 1 is too big. So there's no number between 0 and 1 that's an integer that would solve this. But rational numbers there are. This is the rational number 1/2. Because 2 times 1/2 is 1. So we need rational numbers to be able to solve equations. Another use of rational numbers is a partition. So for example, 1/4 of my paycheck goes to gas. That's pretty believable these days with gas prices, right? So it's a portion, out of the whole amount of something, a certain portion of it, a partition of it goes towards a certain item. So this would be an example of a partition. Ratio. Ratios are another use of rational numbers. So we'll do an example of one that's familiar to you. The teacher-student ratio is 1 to 12, for example, and we would write it as 1 over 12. That's a use of a rational number. And another one that we will encounter toward the end of our semester is probability. So something like this. For a standard 6-sided die, the probability, right, means like likelihood, of rolling a 4 is 1/6. One side out of 6 is a 4, so it's a 1/6 probability. All right, so we're going to look at some diagrams and talk about what portion of the diagrams are shaded. So I want you to take a minute, look at these 4 pictures on your paper. Hopefully they're shaded in the paper pretty well. I think so. And I'd like for you to write down what you believe the answer is to this question for each of the 4 diagrams. The fraction is representing the shaded portion. So take a minute and write those down. Once you're done, I want you to turn to a neighbor and compare. So you really do need to write something because you can't compare if you haven't written anything. If you're wrong, you can always scratch it out or erase it. It'll be just fine, I promise. If your answers differ, talk about why you think one makes sense or the other one isn't quite right. All right, let's see where we are. What did you decide A was? 1/6. So if you were working with students in a classroom, what are some possible things that they might say? Something else they might think that this would be shaded and that would be the value instead. They might say 1/4. That's probably a common mistake. What would they be doing if they thought this was 1/4? Yeah, counting the boxes. Why would that not work on this diagram? Boxes are not the same size. So what could we do to help this diagram look more like 1/6 so that we could explain to that child why it works? Yeah. Right. So if we drew some lines in from the bottom, on the bottom box from the top, and we actually made equal size boxes, that would help this, right? Yeah, it would. So we end up getting 1/6. How about on B? It's 1/4. Now, this one might even be more likely to be told that the answer is not 1/4, but instead what might a student say? They might say 1/5, right? And this one we can't just throw in a couple extra lines in order to fix it, quote unquote. What would we have to do to show that this is really 1/4 to explain why? Okay, so I think you're wanting me to do something like this. Eliminate those top 2 lines. And then what was it? All right, and then split it right here. Did anyone else think of a different way to do that? Because there's at least one more way to do this. What do you have? Okay, so you've written it that it was 1.5 over 6. So how did you get to there?
I
Okay? Do you guys see the 1.5 over 6 present there? Yep. That's another way to express it. And if it's not asking for a simplified form, it'd be okay. You could also do something like this. Make a bunch of little boxes that are equal, right? You could do that too. If we did it like that, what would the fraction look like? 3 out of 12. And if these answers are all, right, they all have to be equivalent, and they are. They are all equivalent to one another, different versions of the same thing. Good job. How about C? 2/7. What might be a common answer that somebody would give on this one? What's that?
I had a lot of students do the other way, like they take what's not shaded.
So they might simply answer the question backwards and look at the non-shaded portion. Okay. Any other ideas? What object in our immediate environment does this look like? Say it louder. It looks like a pizza. How many slices are usually in a pizza? 8. So if a student is using some sort of prior knowledge, they might look at this and see the shaded parts too, and simply assume that there are 8 because of a completely not their fault kind of thing, right? They're using something that's in their prior information and trying to make a connection that doesn't quite work there. And that happens sometimes too. So something to be aware of when a student does something, that there might be a prior knowledge issue. How about D? Yeah, 7/12. And this one is uniquely different than the other 3. The other 3 have an object that's been broken into pieces, right? But this one on part D is like a collection of a bunch of objects, and we're comparing them. So we'll talk about these 2 differences in the way that these are shaped when we get further along in this chapter. Maybe this section, I can't remember. But we're going to stop there for today.